Okay, so we're going to start our lesson on the fundamental theorem of calculus part 1. We already did part 2, and now we're going to go back and finish part 1. And we'll see if we can make this video in less than 30 minutes, okay? Okay, we're going to start by asking the question, how are derivatives related? And this is the fundamental theorem of calculus part 1. So you can go ahead and pause the video and copy that onto your notes. That would be a great idea. What this theorem says is that if a function is continuous, and that's sort of the condition that has to be true in order for the theorem to be applied. If the function is continuous on a specific interval a to b, then the antiderivative, which is equal to the integral from a to x of f of t dt. And remember, we did that little worksheet in notes, which we discovered that the antiderivative and the net area under the curve were the same thing. So this situation, this antiderivative has a derivative at every point in the interval a to b, and this statement is true. And this is sort of the big idea that we're going to be exploring in the video right here. Now I want to just take a moment and explain what this means. First of all, we have the net area from a to x, or the integral from a to x of the function f of t dt. And what we're essentially going to do is we're going to take the derivative of this integral in terms of x. And what this statement is saying is that if you take the derivative in terms of x of an integral that goes from a to x, the result is simply the function you started with, f of x. So this is what this means. The derivative of capital F is the antiderivative, remember? So if you take the derivative of this, of capital F dx, that's the same as taking the derivative of the integral. Those two operations undo each other, so they are inverses, and you're left with the inside only. So what does this all mean? Well, basically it means two things. First of all, it says that this net area is a function, and we had already explored that with fundamental theorem of calculus part 2. It has a derivative, and this also means that any derivative has an integral, okay? And so here we go. The derivative of a function that is in terms of an integral will equal the original function. And it'll make sense in a moment when I do an example. So what does this all mean for us? Derivatives and integrals are inverse operations. That's what this whole thing really means. If you take the derivative of an integral, it cancels. The operations cancel, and you're left with f of x. So you basically, it's like taking the square root of an x squared or squaring a square root. They undo each other, and you're left with just x. So you're going to think of this as taking the derivative of the integral. You basically cancel this out, and instead of f of t, remember, the original function was really f of x. T was just that sort of dummy variable that we used because x meant the stopping point of the area. And so really the function was f of x. So you plug this x back in here, and that's it. Okay? Now it's not going to make a whole lot of sense until we see an example. So let's go ahead and try the first one. Now I'm going to do this one a little bit different. I'm going to do it the long way, and then I'm going to show you the short way. And I'm only going to do it the long way so that you see that it works. And then from there on, you're going to use a shortcut every single time. So here we go. This is the long way. What this statement is saying is take the derivative of each integral. This d dx means take the derivative of the stuff inside the parentheses. Well, the stuff inside the parentheses happens to be an integral. So first, the long way is going to be this. We're going to go ahead and evaluate this integral from 3 to x of 2t dt. We're just going to do it normal, like we've been doing in the past. And then we're going to take the derivative of what we get when we do the antiderivative, and you're going to see what happens. So let's just ignore this derivative for a moment and take that antiderivative. Take the, integral of 2t from 3 to x. So we're going to start with the antiderivative of 2t, and that's just going to be t squared. Okay, derivative would be 2t, so we're good. And we're going to go from 3 to x. So the result is going to be x squared, and then you plug in your 3 and square it, plus 9. That is what the value of this integral is. So now we're going to go ahead and take the derivative of that. And the derivative of x squared plus 9 is simply 2x. So if I take the integral of the inside and then take the derivative of that resulting expression, I really just get 2x. And that's the long way of doing this. So that means that the derivative of the integral of 2t from 3 to x is 2x. And that was a long way. So what's the short way? Well, it's what I told you earlier. You know that the derivative cancels the integral, so basically they undo each other. Just take the x and plug it in for t, and you're going to see that the result is simply 2x. And I know that sounds really too good to be true, but that's really what it means. The derivative cancels the integral, so simply plug in your x, and we get the same answer. Okay? Let's see a second example. Make sure you understand. So again, we're taking the derivative of this integral in terms of x. So the short way. And I told you I did it the long way so you could see that yes, this works. But once we know the shortcut, let's use the shortcut. The derivative of an integral cancel each other out, and then you just plug in this x. So the answer to this problem is C. That's easy. Now, you're going to ask, well, what happened to this negative pi? And what happened to this 3? Well, if you remember, both of these are constants. And when we evaluate that integral and we plug in the 3, you're always going to get some number. In this case, we got 9. Well, when you take the derivative of a constant, it's always 0. So think of evaluating the integral. It would have been sine of x minus sine of negative pi. Well, sine of negative pi is an actual number. It's going to be 0. And the derivative of 0 is still 0. So that's why when one of the boundaries is a constant, it sort of just disappears, because in the end, when you take the derivative of a constant, it disappears. Okay? Let's do one more example. In this example, it's a little bit interesting because the boundary has been switched. The x is now at the bottom and the 2 is at the top. Well, this is going to result in 0, but we're subtracting, so there's going to be a negative involved. To make this easier, I always tell my students the following. I think you guys understand this method already from the explanation before. So what I would normally do is I would say, all right, what I'm going to do is flip that boundary to 2 and then x. It's still 5t dt. But because I flipped the boundary, I have to change the sign of whatever I get. So you have to put a negative, and I always put the negative outside. Okay? So now, excuse me, you take the derivative of that. The derivative cancels the integral. You plug in your x, and the answer is 5x. But remember, you have this negative, so negative 5x. And we're done. That's the answer. So yes, you basically plug in your variable, and that's it. Your x into your variable, and that's it. So I'm going to go ahead and cut this video short because we want to keep it under 10 minutes. In the next video, when you're ready, in the next video, what's going to happen is we're going to make both the top and the bottom boundary variables, and that gets dealt with different. If one of the boundaries is a variable and the other is a constant, this is exactly what you do. But if both of the boundaries are variables, then that's a little bit different. So I'm going to go ahead and let you process what you've seen, and then you can watch the second video.